Um, I keep showing this slide because I'm really serious about this. If you have a mathematics degree, if you did advanced mathematics, like if you did analysis 1 or linear algebra, you're probably not going to be challenged by this. So you would probably have more if you went to another session. Of course, you're still welcome to stay and laugh at me, but especially if you did pure math, you're going to be in pain. Because I renamed the workshop to be called Loser Fear of Math, because it's not really about equations, it's really, we have people who just see something with numbers and letters and they just don't know what to do with it. And if that's you, then I'm going to try to help you to deal with this. Oh, I have this also. So who is this for? Like I said, it's easier to say who it's not for, because our community is so diverse that we have lots of people who transition to data science from different areas, and we need you. We need people who are not like me. Like, I look at stuff and I'm like, oh, cool, this is tech. And then we have lots of Elon Musks, and they're doing things that don't really make sense for the society. So we really, really need people who come from social sciences, from philosophy, and who understand the algorithms and understand what we're doing and help us shape policies and help us shape our industry. So 2 years ago, I held another workshop, which was about rating algorithms, which is actually what I do. And I had this slide, and I spent a lot of time talking about this expression here. And I thought, wow, cool, I did a good job. Everybody understands it. This is awesome. This is easy. And then 2 minutes later, somebody said, but sorry, can you say again, what is n? And then I realized I'm coming into this with a massive privilege, because I've been doing mathematics on paper and thinking about functions and approaching things in a certain way, basically my entire life, like at least 10 years, now 15 with my job. And not everybody has this background. And so we have to try to make data science approachable for people who don't necessarily think the way somebody like me thinks. And this is what I'm trying to do with this workshop. So this is very experimental. I don't know if it's going to work. It's not possible to teach people 10 years of math in one session, 90 minutes. But we can just do some of it. And this is big. I encourage you all to use pen and paper, to do it for yourself while you do it. Like we already said, if you have any questions, it's also going to be a lot of me asking you questions and asking you to think along with me. So speak up at any time. What I love about mathematicians is they have this kind of approach to things where, like, I don't understand this. And they don't go, oh, probably because I'm dumb. They go, I don't understand this. You're explaining it wrong. Explain it better to me. And this is how I want you to be in this thing. If you don't understand it, it's because I'm failing you and I'm not explaining it well. So just ask me to repeat myself. This whole talk is like 90 slides, which is more than 1 slide per minute. So I have absolutely no goal to go through everything. I would rather stop halfway, but everybody got what we were doing, then get to the last slide, but you leave here and you're like, what did I do? I could have had a coffee in the meantime. If you're still wondering why do I need this, I've been wondering myself this whole conference, because, for example, there was one talk I went to, and the speaker just built an entire speech recognition system in the session using LLMs, using open source. He didn't even mention Fourier transform, which, if you work with sound, this is like the first thing you learn, in a mathematical way to convert sound into numbers. So it's possible to apply these things without any technical understanding, and in the last 10 years, the development has been huge. Like, by now, you don't even need to code anymore, not really. But then I went to the next talk, and this was about time series and detecting shifts in time series, and suddenly we had this slide here. And then I was really enjoying myself, because I was like looking around the audience, like, how many people has he lost on this slide? How many has he lost on this slide? Okay, now he lost everybody. And there was actually a question in Slido, can you please explain this cost function? It didn't get asked. But I hope that while we're doing this, in the end, I have a slide where I explain this cost function. So this is also kind of the level that we're aspiring to here. You will be able to understand why this is how it is. And then I went to another really good talk by Catherine Jamel, which was about privacy matters in LLMs. She did a great job not doing mathematics and not showing the paper. That she was actually, there's a mathematical proof about how an LLM is going to memorize some of the training data, which is a super huge privacy concern. And but still, like even this small thing here, like it's nice if you just see it and you understand what it means immediately. And this is, I think this is feasible for everybody. So these are our goals. You look at mathematical expression and you try to understand it. You'll be a little bit more confident and ballparking how a function behaves. Maybe it's just a refresher of mathematics for you. It's not serious, it's not rigorous. So rigorous means I would be defining everything with domains, and I would be talking about differentiabilities and things, and I will not do that. It's too much. And you will need to exercise. So you take this, but then you actually have to apply this. Mathematics is like a language. I think it's a language. So there's grammar, there's expressions, there's rules, and the more you talk it, the easier it becomes. Yeah, so this is the last chance to leave, I think. If you, I will not be offended, I promise. So basically, we're going to look at basic arithmetic expressions. We're going to look at exponents, spend a lot of time on logistics, because logistic functions are kind of the bread and butter of data scientists. And then on logarithms, derivatives we're going to touch a little bit, and then trigonometric functions in the end, if we have time for that. Slide about me, I already had a great introduction, so we can also just skip it. I'm currently a principal data scientist at Bayes Esports. We do betting odds. I studied physical engineering here in Berlin, then I did my PhD in control science. I was kind of trying to get into pure math. Like control science is on the border of engineering and mathematics. Optimal control is a mathematical faculty. Yeah, I spent 2 years trying to prove that a certain matrix has certain eigenvalues. Then I finally gave up and ran a simulation, learned to code, realized it's not actually true. It was a bad day. And then my PhD is explaining why the matrix cannot have positive eigenvalues. Negative. And now I'm here, so. If you want to contact me with questions after this talk, if you want to keep in touch, you can add me on LinkedIn, and I will look at it once a year. I also tweet only when I'm at PyData, because that's the only way to reach out and kind of interact with PyData organization that I like. Otherwise, Instagram is where you find me. It's mostly my jiu-jitsu stuff, but you can message me, and I will definitely see the message. So let's start with some definitions. I called it loosely field of equations. I'm actually going to be talking more about formulas and equations, but just in general, a formula is going to be any string of symbols that makes sense for a mathematician. An equation is then a formula that has equal signs. So this is when we're saying, OK, I'm going to solve for x, so this on the left becomes equal to 5. And then a function is also going to be a formula that's going to now connect an input value to an output value. So for example, here, our input value is x, and our output value, we call it f of x. So when x changes, whatever's on the left also changes. And usually, this is what we're looking at when we are doing data science. And the good thing is we already know it from coding. It's the same thing. When I code a function, I also have an input, and I have something that comes out. It's not always simple. Like, we have functions and equations that can take you a lifetime to solve, like my PhD. Or if you, who has heard of Fermat's last theorem? 2 people, great. So if you haven't heard of it, there is a book, Fermat's last theorem. This is a history of the theorem and people trying to prove it. And I can really recommend it. It's a fantastic read. You don't have to understand mathematics at all to understand how amazing it is. Sorry? Fermat, so Fermat's last theorem. Yes, so in this workshop, we're looking at functions. Functions usually have names. The names can be completely random. Typically, we have something like f, g, h, and so on. And then it depends on the field you're in. Function can depend on 1 or more values. So usually we see f of x, and we're going to stay mostly with f of x in this workshop. But it can also be like the g here depends on x and y. Do I have a pointer? Yeah, I have a pointer, cool. So this means that we can look at how does it behave when x changes, how does it behave when y changes. The annoying thing is notation differs. So people will often drop things for convenience. So you will see something like this, but it's still an equation, but it's still a function, and you know it's from the context. So the same as here, like clearly it's a function, but if you're not used to this, you're going to be confused, which is, I think, annoying. When we see a t, for example, we usually think it's time, but not always. And epsilon is kind of special. Like whenever you see epsilon, you can think this is something really, really small. So one thing is everything is not a dependent variable. So this thing in the brackets here, we can assume to be constant, even if it's written with a letter. So for example, if I actually have examples on the next slide. And a function has a domain. So the domain is just the range of values that our input x is allowed to have. We have the same thing in coding. So if I have a function and it does something with integers or floats, and I input a string, it's going to say, you can't have a string here. So it's kind of the same thing here. Like I allow x to take certain values, and everything that's not in those values is just can't be put into the function. And once again, we're not talking about real math, so spaces, sets, and so on is all beyond the level of this workshop. So let's exercise. The first one, what f of x, what are the constants and what is the dependent variable? Yes, perfect. The second one. C and x, exactly. So I try to trick you. And the last one? And? Yes. Yes. And the function? Yes, perfect. So the last one is basically I replace the f of x here, and then I have 3t plus this expression. So I have a, b, c, and the 3, and the function depends on the x and on the t. And if this was mechanics, I would be thinking t is time and x is position. So we're going to ask 2 questions today. First of all, we're going to ask how does the function behave. That's a different way of saying what values of what outputs do we get for different inputs, same as when we code. And the second question we're going to ask is we have these constants in the function. So can we maybe keep the function the way it is, but by adjusting the constants, move it somewhere where we want to have it? It's going to be more clear as we move on, hopefully. There's a lot more you can do, but we don't care about that. So let's give it a try. So this is the function we're going to start with, quadratic. What does it look for various levels of x? Yes. Yeah, exactly. I'm also going to give you a hack, which I do a lot, is if I have a function, I'm just going to plot it, and I'm going to look at it if I'm not sure how it looks. So here, this is a parabola. It never gets negative. It grows quite fast, on both for very small x and for very large x. And it has its minimum at -1. Okay, great. So some of you have laptops, so you can try it for yourselves. Yeah, so you can. So I stay with this. It's really good to try and plot a function when you want to understand how it looks, but sometimes it's just not possible. This thing, I pulled it off the internet. First of all, I also don't know exactly what it means. I didn't spend time looking into it. But in order to really understand what it means, I would also need to know what is this theta, what is this alpha, what do these things even stand for, which I don't know without reading the paper. So domain knowledge is always going to matter when we're looking at functions, because we're not doing pure math. We're always applying mathematics or something. But why do we need this in the first place? Why can't we just skip all this? Because normally, scientists who write these things, they talk to other scientists. So they have to be really precise, and when you see a paper, there's somebody or a few people who sat there and they check that everything is correct. And that's why we need to have these expressions in papers. But if you're not in the subject matter, then you don't understand it. And just because you don't understand it doesn't mean you're stupid. It just means you didn't spend 5 years working with this. And so if you are reading a paper and you run something like this, it's probably also okay to just skip it and not think, oh, I'm stupid, but just think, oh, this is not for me. So it doesn't mean you can't read the paper. It doesn't mean that you can't read the abstract. It doesn't mean that you can read the conclusions. You just maybe don't read the theoretical proof that's behind it. But that's okay, because you can rely on people who checked it for you. You're looking like you have a question.
Okay, maybe I'll say out loud. If you have questions, please tell me. We can talk it in the mic, because the people who are attending online are not able to hear what you're asking. So it will be nice also for them to know what is the speaker answering. So just raise the hand. I'll stay in the eyesight.
I can also repeat.
Yeah, or maybe you can repeat.
I think it's probably easier. It's a lot of people in the big room.
That's right.
That was the remark.
Yeah.
Okay, cool. Sure.
So if we're reading a paper and we have these kind of long equations, which I often see, then there is maybe we can skip it thinking it's not for us, but if you're working on an algorithm, you have to be able to interpret it, even if your background, if you're just a computer scientist, you probably forgot all your maths already. But you have to know, right? Because if you're implementing this in an algorithm, in your code, you have to understand this form of proof, right? Because otherwise, how do you cannot take it from this was written for this reason, right? So we cannot ignore it.
So the remark here was, well, but if you have to implement this, then you have to understand it, so you can't just skip it. This is absolutely true. And I'm making a small contribution today to help you to go in that direction. This is exactly what this workshop is for. But also, at a certain level of math, this is actually not as complicated, to be honest. Like, this is something you can definitely learn to read. You'll have to sit down and you'll have to learn mathematics. Like, there's just no way past it, unfortunately. Yeah, maybe before we go, like, for example, without knowing the domain, what do I see? Oh, first of all, I'm assuming there's a P and there's a vertical bar, and we're here in data science, so I'm immediately thinking, oh, probably there's some probability of something, so it's probably going to be between 0 and 1. And then I'm thinking, oh, there's some event, and this event depends on these two things occurring. And then I see that there's many different partial states, because there's a product here and there's a sum here. And then at this point, I'm like, okay, this is, if I need to know more about this, then I'm going to have to sit down with a pen and paper. So this is what we're going to learn to do here. So, like I said, I'm going to stick with this thing, because this is the one I did in the workshop, and I think that everybody, when they leave this room, should be able to understand what n does here. And we will get there, I promise. So before we do that, let's just do some ground rules. So let's start with this one. Who thinks it's 16? Who thinks it's 1? Okay, we have 3 people brave enough to say it's 1, and nobody's 16, so I understand. I also wouldn't want to put myself on the spot in a question like this, but let's just recap arithmetics. Let's start with the first one. How much is this? 7. Perfect. How much is this one? Perfect. How much is this one? 4/3. Yeah, I don't need you to do the decimals. 4/3 is good enough for me. Is it the same as this here? Yes. Yes, it is. So what about this? It's a bit more complicated now. 16 divided by 3. Perfect. And last one, this one? I also don't remember. So 6 times 6, 36, divided by 3 is 12 minus 2 is 10. Perfect. Funny thing about mathematicians, they usually can't count. So we already we applied all the rules already very well, so I don't need to spend much time here. But this is really important. We have the brackets first, then we have the powers, then division, multiplication go together in the same order. Addition and subtraction go also together in the same order. When we write NumPy functions, we already have to do this because the computer is gonna go precisely in this way. So I think everybody's already really comfortable here with this, but I still wanted to have it on the slides. So let's go back to this one. We're gonna do the brackets first, which is 4, and then we're gonna, so this is gonna become this, and then we're just gonna go straight, and we're gonna end up at 16. So it's 16 bro. If you want, if you'd like to have an exercise for yourself and go it together, you can rewrite this to make it 1. And if you're in trouble or in doubt, just pretend you're a Python algorithm. So just go straight. What's important for us to remember is when you have addition and subtraction, these happen last. So if you have something complicated plus something complicated, then these are 2 separate things. And we can look at them separately, and then maybe in the end we're going to compare them, but this is already splits our complex functions into parts. So what does addition actually do? How do we understand if we have this plus in our function? If we're adding something, so this is our function here, is y of x is x plus 3. It's pretty intuitive. We have 3 x apples, we have 3 oranges. Now we have x plus 3 things. And so if we add a constant value to our function, then we're just going to move the function in space. So here is an example. 3x plus 5 is the blue line. Is anybody here colorblind? Cool. I went to the lightning talks yesterday, and I was like, oh, shit, I did not think about this. So 3x plus 5 is going to be our line here, and then we just add 5, and it's just going to move in the same direction. And it's the same thing here. It doesn't look like it, but it's still a constant of 5 everywhere. So here, optics fool you. Anytime we add or subtract a constant value, we just move our function in space. Also, the sigma here, you see it sometimes. This is just an abbreviation for addition. So if I have a sum like A1 plus A2 plus A3 plus, I don't know, A27, then I can also write it as a sum of I goes from 1 to 27, AI. This is all it means, just an abbreviation. So every time you see this, there's a sum happening. If we don't have any questions so far, let's go to multiplication. So if I'm multiplying, now things become a bit more difficult. So now my f of x is given by some constant b times x. If b is larger than 0, actually is larger than 1, then it's super simple, and we all know this. Like, I take 6 x oranges b times, now I have b times x oranges, so it's more. As long as our x is positive. So if we are going in the negatives, then I think also everybody knows this, but just recapping, multiplying a positive by a negative is going to give you a negative number. So this is why here's our function 3x. It's positive, from 0 it's positive, and then once x becomes negative, it's going to go into the negatives. And all of our multiplicative functions pass through 0 because anything times 0 is 0. So what it means is we have to pay attention when we have our x here, which values can x take? Because the same function can be positive, can be negative, it can become 0. And sometimes this will change everything for us. And again, the same as we had the sigma before. If now we were multiplying our a's instead of adding them, we would write them as this product. So remember in our big scary equation, we had products and sums. So it wasn't actually that scary. It was just products and sums of things. Division. Now we're getting into territory where we have to be a bit more careful. So as long as so f of x is a divided by x. So a is constant, I'm dividing by something that's changing. So as long as a is larger than 1, we're perfectly fine. I have my cake, I'm dividing it into x pieces, the pieces get smaller and smaller and smaller. So here we get closer and closer to 0. It's very intuitive. But if x is between 0 and 1, this is where things actually exploding, because now I'm dividing my cake by half pieces, so I'm actually multiplying the pieces. So the closer I get to 0 on the x-axis, it's called x-axis because it's the values of x, the larger actually my division becomes. And finally, I cannot actually get to 0. I'm not allowed to divide by 0 ever. So this is why we see this asymptotic approach towards the axis, but never touching it, except when you work with NumPy. NumPy will, if you try to divide by 0 in NumPy, you will see, warning, you're dividing by 0. And we'll just put an infinity. And suddenly, you have divided by 0, you didn't even know this. And in reality, you did something that you never were allowed to do. One thing where it happens, where you can notice, is if you had integers, suddenly you have floats. You probably divided by 0. It's a very high chance that's what happened, because infinity and also nonce they are float types in NumPy. So you have to be a bit careful there. What do we have to remember from this? Division is inversion of multiplication, but we can never divide by 0. The other thing we need to remember is multiplication of two negative numbers is positive. And also, I would like to remark that there's a billion ways of writing division, which are all the same. So also, there's this star here. Obviously, we don't actually need it. We can drop it. But this all means the same, especially this a times x to the power of -1 is just a fancy way of writing this. So when you see negative exponents, this is what it means. It's like I said, mathematics is a language, and this is the vocabulary we have. So these are the things we need to know. Any questions so far? Cool. This is mean. This is a bit longer than the other two. So actually didn't really do the math, to be honest. Yes, you had to. And then we can simplify it to 9/12, so we can simplify it to 3/4. I think, no. Yeah, doing live math is like doing live coding. So, and all this is wrong, and so on. I just wanted to point out that if you have this big division, then this thing just flips and goes up. And also, just to have some fun. Like, you probably never have to do this in real life. So now this is our algorithm of how we're going to apply everything we just discussed, remembered, recapped, to every single function we're going to meet. First of all, we're going to ask ourselves, what kind of values can x take? Then we're going to ask ourselves, can we split it into parts with just plus and minus? Then we're going to ask, is there division? Can this thing become 0? Where do we have to take care? Then we're going to see if they have constant factors that we can just lump together and ignore. Then we're going to see what happens if x becomes 0, if it's allowed to become 0 in 1. If not, we can just skip this. Then we can see what happens if x is very large. And finally, we're going to see what happens if x is negative, if it's allowed, and if it's very, very small. And we're going to execute this every single time. So let's start with this example. We did this before. So the domain here is not defined. We can use anything. Yeah, these parts, there's like 3 different parts. There's no division. There's only one constant factor. If x is equal to 0, then this thing is equal to 5. If x becomes very large, then this term, the power term, becomes the largest, so it's going to be dominating the whole thing. And if x becomes very small, we have a power of 2. I didn't say this before, but you would probably know this. It's also going to be positive, and it's also going to be very large, so it's going to be doing the same thing. And then we have this parabola that we already saw in the plot. To formalize this, you sometimes see this expression. I'm not sure how to say it in English. I think it's Limes still. In German, it's Limes. It is basically just means what happens to my function when x becomes some value that's written here. So, for example, this means what happens if x becomes 0 or goes towards 0 if it's not allowed to become 0. Normally, we're going to see 0, infinity, minus infinity, because these are the most interesting parts, with exceptions. So again, like vocabulary, this is just fancy notation for asking this question. So yeah, so this is just another slide saying the same thing. So what happens for different values of x? What happens for, this is our algorithm again here. Let's do the first one. Any takers? Yes, x not allowed to be 0. Perfect. Can we lump constants together? Yes, somebody said the bigger k is, the furthest will be away from the 0, 0 point. So the 0, 0 point means, so if I'm drawing, I'm going to have a x, I'm going to have my f of x here. So this is 0. So if k plus m equals to 1, then I have 1 over x, which is something like this. And then if k is larger, I'm going to be dividing a larger thing by x, so I'm going to be coming more here, and so on. What happens if x is under 0? Yes, we're just going to flip the sign, so we're going to be here. Let's go to the next one. Same thing. First of all, here we have some additional condition, which we need to have, because otherwise we're going to be dividing by 0, which we can't. Number 2 is fine. There's no parts. The divisor can't become 0. Can we lump together constant factors? Yes. So this is just some number. And then we just have x times some number. Sorry. So question? Is it this like this? Or is it like this? Depending on n. Thank you, sir. Question? Mm-hmm.
Maybe a little just time for thinking and
Thank you. Thank you for this remark. So the feedback from the audience is, I'm going too fast. I'm not giving people enough time to think along. I'm sorry about this. Let's go a bit slower. So let's take this one.
Can I ask a question?
Yes, question.
N is something for natural numbers. So is it a bias to consider n is always larger than 0? Because that's why I said it's like this.
I wouldn't assume anything. So the question was, n is something like natural numbers. Can I assume n is always positive? No, you cannot, because it really depends on which field you end up in, and can mean whatever. So natural numbers are going to be written like this. Like this is a set of natural numbers. Then, if you see this, then you can be absolutely sure this is natural numbers. Yes.
Question about the second equation.
Yes.
Does it always go through the origin?
Question about the second equation, does it always go through origin? Can anybody answer this question? Yes, yes, you can answer. Yes, it goes. Yes, it goes. It always goes through the origin because when x becomes 0, any multiplication becomes 0. Thank you. This was a very good question.
Sorry. The second equation, I forgot. If you have a multiplication and a division, which one goes first?
They are the same priority, so we just go left to right.
Okay.
So we're just going to go x times n divided by k. But also because they have the same priority, it doesn't matter if I do am I it's the same, right? Yeah. Yeah, it's the same.
Maybe a quick comment, because for online people it's very difficult to follow what is going on this whiteboard with the marker. So I'll just move this board to the left hand side where there is more light. And just a request to you, when you're writing something, please make sure that you're not also like hindering the camera vision. So online people can also see.
Okay,
sorry to interrupt.
I didn't know there were online people. Hello, online people. I'm going to skip the rest of the exercises just because of time. You're very welcome to do them for yourselves and show me your answers after. As you saw here, what I did actually is every time I talked about it, I also drew it. I think this is super helpful to draw for yourself the functions, because this way you can actually understand, at least for me, myself, I don't think in curves, but if I draw it, then it becomes much simpler. And maybe could I stand here? Is it fine? Okay. Just maybe the last one. Let's just let's say I have no idea how this looks. Then I'm just gonna go, okay, let's say x is equal to 1. Then I have 1 over 1 plus k, and I'm just gonna put some number just for myself. I'm going to say, okay, let's say k is equal to 3, just for now. So I'm going to say, okay, let's say x is 0. Then I have 0 over k, which is 0. So I'm going to have a dot here. Let's say x is 1. Then I'm going to have 1 over 4, which is here. X is equal to 2. Then I have 2 over 5. So it's going to be somewhere here, and so on. And I'm going to just execute this through, and I'm going to do the same on the negative, kind of like the function I showed before for myself, until I get, okay, maybe now I understand how it looks. You know, you can't always do it. Sometimes it's going to be too complicated. Sometimes I also just don't know how a certain operator behaves. But oftentimes this is going to be good enough. And like we had before this question, but I have to understand this, even if I don't know it. This is what I'll do. I'll sit down and I'll actually work through it piece by piece by piece until I have an intuition about what it does. And the only difference between people who studied maths and normal people is they just did this for years, and years and years and years, and they became very, very comfortable with doing it. That's all. Question? Yes.
So when you have your first glance on any equation, like do you try to substitute like in your mind, or do you look at like certain, like what is it, division? Is it like an exponential, and then based on that you try to get like the first impression of how it would look?
So the question is when I personally, or a person? Okay, somebody. And I'm not a mathematician, just to be very clear. I have a PhD in engineering, not mathematics. I wish. And so do people look first? Sorry, can we use a microphone? I don't think I can repeat the question adequately. Sorry.
Okay. So I was saying, like, when you try to have, like when you have a first glance on the equation, okay, in order to understand it, like, do you try to substitute with numbers, like x, x is equal to 1, then y would be this, x is equal to 0, then y would be this. I mean, in your mind, and to get like the first impression of how it would be looking. Or do you rely more on the patterns, like this is a division, this is a multiplication, this is a constant, and then, okay, I think this would be exponential, or this would be like that?
So I can't speak for all people. I think people are very different, and the way people think is also very different. Me personally, I do this. Like, I do this with anything. Like, the first thing I'm going to do is actually number 3. I'm going to see, can there be a division by 0? Like, this is always the first thing I'm doing, because I think it's the most important one. And then I'm just going to go through all these things. Another step that I might have to add is, if I see something I've never seen before, then I'm going to look it up first. But and it's also not fail-safe. So if we have enough time, we're going to go to parts where intuition fails us. But I think, again, it's good enough, and good enough is what we're striving for in AI most of the time. Does that answer your question? So this is a real-life example, which looks scary, but actually isn't. This is the PageRank algorithm. Like, who here has seen PageRank before? A few people. Cool. So let's just look at what D does. But first, normally a function doesn't just come like this. It comes with an explanation of what the actual parts do. So here we have the I, which is our all pages that link to P. Page rank of a page P. So P is not probability, P is just a page. It's given by this plus D times, this is the sum. We talked about this before. So it's just a sum over some pages I. And each page has its own page rank. And then the page has some number of links to our page that we're looking at. And then this thing converges and things happen. For now, we don't need to understand what exactly happens here. I just want to talk about what does D do. So how do we approach this? First of all, what domain can D have? This is something, it's kind of domain knowledge. It's a bit common sense. I have 1 minus D plus something times D. So normally it's going to be between 0 and 1 here, right? Yes. So, and the parts are connected by division, by addition. The division here is irrelevant. We can assume this is positive. What happens if D is equal to 0? Yes, the second thing goes away, and it's just 1 over n. So 1 over all the pages. So completely random. The probability, the page rank of page P is just 1 over all pages I have in my corpus. What happens if D is equal to 1? Yes, the first thing is 0, and the second thing is the only thing that matters. And so what does D do? Yes, it balances between our parts of the algorithm. So not everybody here raised their hand saying, I know what PageRank is. So I hope now everybody still understands the function of D in this algorithm. It just takes some constant value and balances the importance of this versus the importance of the actual algorithm. Yes?
This is actually an example where math
Wait.
becomes quite...
Wait.
So I've been doing machine learning for a while, but this is a good example of an equation that becomes very mind-boggling for me because it's recursive. Mm-hmm. Could you comment on that? What can I do when I see something like PR depends on PR of something else?
So recursion is something I have trouble with myself. I'm a firm believer in not having recursion in your code ever. Is it a trick question? Do you have an answer? Do you have a good answer?
I think that is a good answer as well, acknowledging that it's scary, probably not only for us.
So I read about this algorithm when I was preparing the talk. Basically, I know it's going to converge at some point. And when I look at this, I start with the finished product, and I kind of think back. So where did we start from? So in the beginning, there was just some random rank that the page had. Probably all the pages had the same rank. And then I imagined, OK, now we're chugga, 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 chugga. This went on for a while. And then they probably went to different directions. That's how I visualize it for myself. Also, this gentleman teaches machine learning, so maybe he has a better answer to this.
Yeah, I mean, a different way to express this is the eigenvalue thing, but I don't think that helps, because I find eigenvalues scary as well.
I love eigenvalues, but it's not part of this.
Then I give you the mic back.
But it's not part of this talk. No linear algebra in this talk, unfortunately. But another question.
Maybe I missed it, but how did you come up with the notion that D is between 0 and 1?
Domain knowledge.
So I didn't read it, yeah, that's my fault. So the side comment was, it is defined, and yeah, it says probability, yeah. So
no worries. Like, this is a safe space, there are no stupid questions. I love that you had this question, because it's actually super important, and it shows us that we have to question everything when we look at formula. Like before, we didn't make assumptions about n, and we also can't make assumptions about d. It's also d because it's dampening in this case. Okay, bad news. But bad news number 1, we're not going to do any of this probably. Bad news number 2, you have so many different ways of notation that depending on which field you come from, you're going to be confused, not because you don't know something, but because you just never seen how they write that. And I like this. I also use this. And this is just like, why? But yeah. We also, we're back to our friend, the big equation, which now, remember, you have the product and the sum. We already saw we have different ways to write division. People will also use whatever to replace Greek letters to save time, because every time, so these slides are made in Google Drive. Every time you see math, I either went to Wikipedia and copied it, or I opened Jupyter, made a text box in Jupyter and wrote LaTeX in the text box, and then I made a screenshot and I copied and pasted it over. I'm pretty sure there's more efficient ways to do it. I'm just old. But that's why you will see sometimes, for example, in the normal distribution, you have this, but for scale, but people also, sometimes will just write S, and it's imply you just do it in your head. And also intentionally in these slides, I'm doing it sometimes for you to be used to it. And also different fields will have the same name for different constants. So again, this is really, I really liked the question before, because you really have to read the fine print if you want to understand what's what. And different fields have different notations for the same operations even sometimes. And also combinations of constants are often just abbreviated, and then you are left to find out for yourself what it means. So unfortunately, it's not always all very reader-friendly. So this is our real-life example. Both of these are from Wikipedia. One, for some reason, is a big F, one is a small f. One is written f of x, one is written f of x semicolon, and then 2 other values. This could also be f semicolon L and k and x0, but it's not. So approaching these functions, Which domain? The domain is not specified, but is there any value of x that the function cannot take here? Sorry? I'm not sure what you mean. No, sorry. Like this actually only just means that f depends on x, but you can also modify the values of mu and s in this. That's really all it means. So actually, I don't even want to do this. I just wanted to point out that if you look at this closely, you can see that this is the same function. So if I'm going to set L to 1, and I'm going to set S to 1, and then the one on the bottom becomes no, sorry. Doing mathematics live. So we have, and we have on the right, on the bottom. So in order for this to look the same, I have k equal to 1 over s, and I have mu equal to x0. So now if I put 1 over s here, this becomes and then if I replace x0 with mu, this becomes which is the same as this, right? So the connection between the two functions, just call it big f of x and small f of x, is I set L equal to 1, k equal to 1 over s, and x0 equal to mu. And it's basically the same function. So they look completely different on the first glance, but they're just variants of the same thing. Does this make sense? If it doesn't make sense, do you just need more time, or do you need me to explain it again?
20 minutes more time.
Then I can follow.
Okay. I'm already failing you, everybody. Okay. Maybe if you want, like if you really want to understand this, you could. I'm going to put the slides online after, and you could just take it home with you and sit down with pen and paper, and just do it for yourself. Like, what can I substitute my constant with to go from this? To go from this one to this one.
For the first one, between the braces, what does the notation exactly mean? Between x and...
You mean this semicolon?
It's not dependence, right?
It's not dependence, no. So this is just basically telling you, okay, x is the variable I'm actually inputting, and then mu and s are parameters that I can adjust in order to modify how the function looks. Moving on, just powers. Powers are super important. So here already we had a power, e to the power of something, which is why I didn't want to go into this algorithm yet. Taking a to the power of x is just taking a x times a times a times a x times. So it's kind of an abbreviation again. So let's play it through together. What happens for different values of a? So what happens if a is equal to 0? So we have a is 0 and a is 1. So 0 times 0 times 0 times 0 is always going to be 0. What happens if a is large? It's going to explode, yes. What happens is if a is very small? So cool. I have two options. I have it's going to get super small, and I have it's going to get approaching 0. That depends on how you call very small. Is very small. So very small can mean this is 0 here. Very small can mean I'm going towards 0, or very small can mean I'm going super negative. So be careful when people say something's getting very small, because it has two different meanings. So if A is negative, then I have to know the value of x. Because we have one important rule, which is if x is even, then we have negative times negative, positive, times negative times negative, positive, and so on and so on. So a positive power always gives us a positive value of the power. And this is when we have curves like this. Remember before we had a quadratic equation? And if we have a negative, an impair number of powers, then no matter how many, so then we're going to have positive times A times A. Positive no matter how many times. Positive. And then the last guy is going to be a negative. And this guy is going to flip our entire value of the power. So this is when we end up with something that as soon as A is negative, flips on the other side, but otherwise looks the same. And I think I said this before, if you see something to the negative power of something, it's just fancy notation for division. So what's really important is 3 to the power of x is not the same as x to the power of 3. Because as x grows, it's just multiplication. So I'm going to have 2 times 2 is 4 times, or 3, sorry. So yeah, let's say x is equal to 2. Then I'm going to have 2 times 2 is 4, times 2 is 8, and so on and so forth. But if I take 3 to the power of x, then it goes times. Then with every value of x, I'm raising the number of times I'm taking this power. So like here we go, the value range here is between 0 and 7.5. It's not that much. And our x to the power of 3 is super small, and our 3 to the power of x is already like by 20,000. So this is why when we say we have exponential growth of something, it's usually a bad thing, because it goes super fast, super high, super fast. It also means for us that if we have 3 to the power of x plus x to the power of 3, then already when we are at 7.5, we don't really care about the second term anymore. We can just look at the big one. So things to remember: taking everything to the power of 0 is always going to be 1. Another thing to remember is if you have an exponent, it applies only to whatever it's attached to. So if something's in brackets, then it applies to the whole bracket. But if it's not in brackets, then it just applies to whatever, like here to the 2. And x to the power of 3 is very, 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 very different from 3 to the power of x. And 3 to the power of x is the one you should be worried about. So yes, so this is a formal version of what I just said. Limits of x versus infinity of x3 plus 3 to the power of x is going to become 3 to the power of x. And finally, the pair and impair exponents, which you can remember if you remember this year. Any questions? So we still have our algorithm. We're going to add another step now, which we check, do we have any exponents? And are they in a very late value range where the result is small, or is the result large? And can the exponents get negative, which would lead us to a division? So let's try this guy. to the power of 5 minus x divided by 20. So are there any values x not allowed to take? No. No kind of division subtraction. Is there division? Yes, but it's constant. It can never become 0. Perfect. Constant factors we can't lump together. What happens for x equal to 0? Yes, it's just a constant value f. So it's write it like this: f of 0 is equal of 10 to 520, which is the same as 10 to 1/4. So square root 2 times. I'm ignoring square roots in this workshop, but you're correct. So it's something small. So it's smaller than 10.
Maybe sometimes it's easier actually to do some math, because for example, when I plot it in my head now, I actually do simplify it. So because you see that you can simplify the problem, and then it's just a hyperbola, and then you move it with the constant. I'm not sure like what is the best strategy to follow the algorithm, like in a while, maybe yeah, it is, but sometimes maybe having some math and simplifying stuff also helps.
So a comment from the audience is you can also just simplify in your head, and then you don't have to follow the algorithm. You can just make it easier for yourself. That's true. The thing is, we want to do more and more and more complex things, and that's why I'm powering through the entire time. But you're absolutely right that sometimes things are straightforward enough that you just see what happens. And sometimes you can also simplify. And yes, you can divide. So this is, yeah, of course, I can also, no, actually, no, I can't. Never mind. So what happens if x becomes very large? So constant, yeah, another remark.
There's an interesting point that jumps into my face when I look at this, when x is exactly 5.
Yes,
that helps.
Yes, perfect. This is what happens in that point when x is exactly 5. Yes, because it's 0 to the power of 20, which is 1. All our exponential functions always going to go through 1. Just super cool. And if x is very large? Yes, so if x because we have something negative here, so we have 1 over 10 sorry, like this. And this is going to be super, super small, approaching 0. And what happens if x is minus? Sorry, 1 minute for everybody to look at this.
I'm not following why we get 1.
So x is really large. So 5 minus x. This one? This one we just all agreed that this is going to be the case. Because x to the so we have something to the power of 0.
Then we have 10 and exponent 1, which is 10 and not 1. No, 10 is 0.
So 5 minus x, 5 minus 5 is 0. So it's 0 over 20, which is 0. And so it's 10 to the power of 0, which is 1 by definition. So what happens if x is very small, and by this I mean very negative? So So now I have something minus something negative, which is positive. So I can write so it's something really, really large. So the 20 becomes completely unimportant at some point. It's just going to be something completely huge. It's going to be, and I plotted it. Here we are. So this is a 0. And you're right, we were right. The closer we go, the more positive we get, the closer we get to 0. We never get to 0. And then the more negative we get, the more we go. And this is just zoomed in between -10 and -7.5. We have like this approach here. So we just did this ourselves in our mind, which is what we aspired to do from the beginning. Moving on, let's do this one. So we already did this bit, but now we add another division to this. So let's work off what we already know here. First of all, we remember that for 5, this will be 1. So what does the whole function take for x equal to 5? 1/2. 1/2. So we know that if x grows large, this whole thing gets very, very small. So what happens to this one? Very close to 1, correct. And now we know that if this gets very negative, this thing gets huge. So the whole thing gets to 0. Cool. Do I have a plot? Yeah, okay. Now, what did I do? Instead of a 20, I have a 200 here now. Yeah, that's exactly the question. That's exactly the question we have to ask ourselves. So, how does the 20 modify our speed? Because everything else, the shape is going to stay the same. The 20 for large values and for small values doesn't change anything. Can everybody see this? People are nodding. The 5 is the same. So where the function goes through 1 also doesn't change. The only thing that changes is the kind of the shape of it. If you plot both next to each other, this one is the 20, and this one is a 200. If you homework, sit down and work through why the 20 is steeper than the 200. And now remember in the beginning, we had on my slide, I had this function. It's the same thing, except the 5 is now the RA, the X is now the RB, and the N is now, and the 200 or 20 is now the N. So it's going to behave the same way. It's also, like all of these are logistics, so they all go between 0 and 1, which are the logistic function, which we use all the time. And they all go through 0. Through 1. They all go if there is no constant here, then they all go through 0. Then depending on how the divisor here is, they're going to be more or less sloped. And then depending on which value you put here, this is where we're gonna. This here is gonna shift. So now, so instead of 5, if this were 0, then it would be for x equal to 0 is going to be equal to 1, and so on. Yes. You're right. This is a mistake on the slides. This should be f of RB and not f of x. This is completely my fault. So, what's the difference between this one here and this one? The x is now in the divisor. So what do we immediately say if we see this? X cannot be 0. Thank you. Please, please, if you remember one thing from here, remember that you see this and you scream, x cannot be 0. So I had a really good comment as well. So here you said x is 20 does something special. So if x is equal to 20, then we have 1 over 1 plus 10, 20 divided by 20, which is 1. So it's 1/11. So we know our function is going to go through 11, or 1/11, sorry. What happens if x gets very large? It's half. So 20 divided by something large is going to be almost 0. So this is going. So 10 to sum to 0 is going to be 1. So it's going to be half. Perfect. And what happens if x is very negative? I did not remember that I put all of this on the slide, but yes, it's also half. We end up with this thing. And this is where NumPy fools you, because it just draws a straight line here. There is no straight line. 0, this function is not defined for 0, but NumPy just goes, yeah, whatever, and then Matplotlib just also goes, yeah, okay, I'm just going to connect the dots. So be careful here. I did have a fat pink warning, you're dividing by 0, but I also all the time have fat pink warning, you're setting with copy or your data frame, so I just learned to ignore the pink warnings, and then this happens.
But there is a trick if you don't use a plot but scatter.
Yes, if you scatter, also if you cancel the line and just plot the dots. Okay. Can we finish this? Can we move on? We only have 15 minutes left. So, my first time teaching this ever. I ran a version with my colleagues, but I changed so much that there's no comparison between that one and this one. But be grateful you're getting this one, because the first time was even faster. Anyway, E. I want to talk about E because you see E and you're like, wow, this probably has some very strange meaning. It's everywhere. People say it's so important. Oh, it does this, and 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 it's just a number. It's a very cool number. It has lots of properties. If you do mathematics, you do beautiful things, but it also has a value. It's irrational, like pi, but it's just 2.71 something, something, something. So if you see e to the power of something, it's just a constant. So you can treat it as just like any constant at all, just like you treat pi. You don't see pi, or maybe you do, but you don't see pi and you think, oh yes, Pythagoras and geometry. You just see, okay, 3.14, oh haha, pi day, and so on. You can treat e the same way. So now we're getting to our logistic function, which is why before I made you do all these different variations of it, so that now we can go back to it. So x0, normally if you see x minus x0, then x0 is just some starting point for value x that it has to have. And then we have some exponent here, and we have some L here. So like not the exact points, but what shape does this function roughly? Like make a motion with your hands. Yes, everybody's showing me the logistic. Perfect. Like all of these are going to have a logistic, and all of these are going to go from 0 to 1, except if I change L. I just multiplied the entire thing by a constant. And as we saw, multiplication just grows the scale of our thing. So now it's going to go between 0 and 2. And then different values of k. We saw before with our 20 to 100. I'm just going to change how slanted this thing is. So, and finally, our x0 is just going to move where we go through 0. So here we were going through 0. Now we set x0 to 2, so we're going to go here So 0.5, so this point shifted. So this way you can understand what different factors, different constants in this function are doing and how they're affecting it. Does this make sense? And so a lot of the time when we're tuning something, then we're just trying to find a combination of these constant factors where we already have a function, but we want it to go through this dot and this dot and this dot, and then we tinker with the values until they do. Normal distribution, another friend. So I think everybody knows normal distribution. Looks something like this. Gaussian, exactly. I heard somebody say that in the crowd. And then depending on the value of mu and of sigma, it's going to be moving around. Just to save time, we're not going to exercise through all this again. But just like this is the one I just drew, which is mu is equal to 0 and sigma is equal to 1. This is the most standard one we see. And then if I change the value of mu in here in this bracket, it's going to shift laterally. And then if I change the value of sigma, I can control how high and how low it gets. And you can go home and you can do the same thing we did before, where we were putting in different values for different parameters, and you can work through it by yourself. So then we have the cumulative distribution function of a normal distribution. So cumulative distribution function is just statistics probability theory definition, where I say, okay, I have the sum of values up to here, sum of values up to here, sum of values up to here, and so on, and I plot this. And I think we had this on a slide before, actually. We were looking at this. And we did the substitution before already as well, all together. And so now we see them here. So this is just the cumulative distribution function of the normal distribution. So this is how the normal distribution and the logistic connect to each other. And again, because of time, I'm not going to do it step by step. But these guys and these guys are basically the same thing. And I hope I gave you the tools to sit down by yourself and understand this. And it will take some time, but I'm sure you get there. I really want to try and get through the algorithm, because I think logarithm is super important. The logarithm is the inverse of power. So the same that division is the inversion of product, and subtraction is the version of addition, or the same, or the other way around. Logarithm is the inverse of power. So if I'm saying I want to have the logarithm of some kind of base, so for example, here I have a logarithm of base 10 of 1,000, then I'm actually asking by what power do I have to take 10 to arrive at 1,000? And in this case, the answer is 3. So 10 to the power of 3 is 1,000. We have different bases. Normally, we use base 2, base 10, and base e, because they are just the most common ones. So base 2 logarithm is binary, which is why we use it. Base 10 is just because we have 10 fingers, so we count in the base 10, so 10 is just our favorite number. And e is a natural logarithm, which is why e is special. And remember, it's just a positive real number, so if I have a logarithm to the base of e, it's abbreviated ln for natural logarithm, but it's still just asking to what power do I have to take 2.71 in order to get x. Why are logarithms important? Before we got there, actually, let's do this exercise. So what's a logarithm base 2 of 8? 3, perfect. Everybody does computer science. What's 16? What's this one? Some numbers, perfect. A lot of the time it's good enough. It's some constant number, right? The reason why we see a lot of logarithms in our life is because we have all these cool rules, all the cool operations, so it simplifies a lot of our mathematics if we just go to logarithm of something. I just took it from Wikipedia, credit. So provided the base is not equal to 1, and all of these are positive, we can apply a lot of formulae that help us do mathematics with logarithms. So this one, the product of, if I have a product of two numbers and I take a logarithm, then I can just split it into a sum. So our 243 that we had, we can split it into 927, which is a logarithm of 9 logarithm 27. So 3 times 3 is 9, so this is 2. And 3 times 3 times 3 is 27, so this is 3. And so it's 5. And this is why people, before we had computers, they calculated a lot with logarithms. Because instead of doing huge numbers, they just had lookup tables, and then they used the lookup tables, and they converted their products into sums. And how we use it nowadays is we have logarithmic scales a lot. And it's important to understand them because, again, we see them in many places. And one example is decibel. So decibel is a logarithm to the power of 10, and it's a relation between some value p1 and p2. And then you take it times 10 by convention. So when do we have 0 decibel? Yes, when p1 equals p2. Then logarithm, so 10 to the power of 0 is 1. So that's when we have 0 decibel. And then if p1 is 10 times bigger than p2, we get 10 decibel. So, and then in order to get to 20 decibel, because this is a logarithm, we're now going to have p1 being 100 times of p2. I don't know what I was trying to do here. So every time that our p1 becomes 10 times more, 10 times more, 10 times more, the decibel value only increases by 10. And this lets us plot it like this. So see, we have 30 decibel, but it's actually, but p1 over p2 is actually 1,000. And this makes it easier to display things that scale nonlinearly. Another real-life example is pH. pH is also actually decimal scale. So I know I've always been confused by decibel. I always have to sit down and rethink this. So maybe if it's the same for you, I hope this helps you now a little bit. Yeah, so this example here is if p1 to p2 is 1,000, then we have a logarithm to the base of 10 of 1,000, which is 3 times 10. So we end up at 3. 3, and then times 10 is going to be 30 decibel increase. So it's actually 1,000 times louder. And that's also why we use log-log plots a lot. So if you've ever wondered why are we using log-log plots, is because if I have something, some function, which is some power function, then in a logarithm it just becomes like a straight line. And so it's easier to compare. For example, here's f of x squared, f of x times 3. If I were to plot them in a normal scale, I would have f of x squared, and f of x of 10. It would just grow so fast that that this one would just disappear. And that's, but in a log-log plot, I can actually see what's going on much better. Yeah, we have time. I think we still have time for this one, and then unfortunately we didn't get through everything I wanted. But I think Shannon entropy is super cool. Yes? 5 minutes. Yes, 5 minutes. That's why. I guess this workshop is a two-parter. So Shannon entropy of a random variable. I think this is a super cool thing, and it has a logarithm. So first of all, it's a probability. So P here is a probability, and E is an event. So we call it the surprisal, which is how surprising is the event, the probability P actually happens. Extreme case, a certain event has probability of 1. So logarithm of 1 is 0, it's 0 surprising. And then the smaller the this value here becomes, the more surprising is it actually happens. So if it's like 0.000 something, then this is going to be huge. We're going up here. And then it's super surprising that the event happened. And we call this information in a surprisal. So this and this is the same thing. With the only difference is that here there's no base, and here there's a base of 2. The base is completely irrelevant for this, because we're only interested in the behavior of the logarithm. So what changed between the two expressions is, yes, I added a base, and I rewrote the 1 over something as a negative. I'm not going to explain it now because of time. So what we're actually looking at is the expected information from random trial. So we have events with a probability, and we get some kind of information. The information is given by this expression. So 2 examples, a coin toss. We have a coin probability 0.5 that this heads, probability 0.5 that this tails. And so the information of this one is going to be the sum of logarithm 0.5, so this one. And then if we have a die toss, then we have 6 different events. So it's 6 times 1, 6, which is, so the chance of each one event is much smaller. So the information we get is going to be larger, because we are approaching this here. Some people are still nodding. I'm really happy that somebody's following. And so the Sheldon entropy is just the sum over probabilities of all my events that can happen times the logarithm, so that times the information that they give us of the event. And let's do it with an example to understand it. So let's say we have a fair coin, then we have 2 principal events, each have a probability of 0.5. So I have a sum over 2 events of 0.5. And we just can calculate this. It's going to come out to 1. So there is not, there's not much information coming from it. But if I have an unfair coin, so probability of heads is going to be 0.7, and probability of tails is going to be 0.3. And again, I'm going to calculate, put it into this formula. I'm going to end up with a value that's smaller than 1, because there's a much higher information in this coin toss. Because the probability of ending up with heads is so much higher than the probability of ending up with tails that I know more about this coin by tossing it over and over again. And this is how people begin to crack code, because now they get information from the binary, the probability of how likely the binary is to express something or not express something. And we end up at this thing, which is also information theory. And unfortunately, I'm so sorry. I was going to do a lot more. I did not. I still hope this was helpful for everyone. I got across my 2 most important messages. I really wanted to talk about logarithms, because I think they're difficult and important. And I really wanted to talk about the logistic, and I want to give you an understanding of how logistics are super easy if you just touch them and look into them. And then now if you go back to your data science bootcamp or whatever got you into data science, and you look at your activation functions, you will hopefully understand why they are the way they are. And you will read this, and you will have a much better understanding of what you're actually doing. And then from this, if you just go back to the slides, yeah, I'm sorry, I didn't do this. Where is the, if you just, sorry. Yeah, here. If you just stick to this, and if you just teach yourself to always do this, you'll be more and more and more and more comfortable, until at some point you just be like, okay, yeah, this is probably like this. Oh yeah, okay, fine, whatever. I have an idea how it looks. Thank you.
Let's thank Darina. Thank you so much. I think it's bold and courageous to even come up with a workshop like this to start with. But of course, with practice, I think as her message, practicing this every day will make us better in understanding. Just one question from my end. Do you have any recommendations for all of them, like to follow any sort of tutorials or anything that helped you understand math better? even for the beginners level? Like any YouTube videos or channels that you specifically would like to recommend?
That's a great question. Unfortunately, no, I don't, because I didn't have to do it for obvious reasons. I had to do it in school. So when I said I want to learn real mathematics, what I did is I got the homework for analysis 1 for mathematicians, and I just worked through it myself. And I think you could do the same thing, but just maybe with engineering. So if you take analysis 1 for engineers, then this will give you all of this and more. And you just have to, but you have to work through it. So if mathematics, you have to sit down, you have to exercise, you have to solve the equations, and then you get comfortable with it. So just get any university coursework and just work yourself through it, and that will give you that.
Okay. If I have your permission, may I recommend one channel that
Of course.
So something that really helped me to understand math better. There is this channel called 3 Blues, 1 Brown by Grant Sanderson, and he's amazing at explaining how it happens visually. Also, Darina helped us to look and start thinking in terms of plots, which is kind of intuitive and at least helps you think what the function is doing, and it's a great start. So I saw one hand raised, so we'll take that as a last question for this round.
I also have a question. Does
sorry.
anybody else have recommendations for channels, books, etc.?
Oh, great. So, yeah, please, I'll just go one by one. First, let's go to the question.
Sorry, what was yours called?
3 blues, 1 green, blue, 1. Yeah, 3 blue, 1 green.
Okay, my question is rather simple. Will the slides be shared and where?
I will share the slides.
And where? Discord. Okay.
Discord. Okay.
Okay, thanks. And was there another one? No.
So we were asking for recommendations.
So I'm a physicist, and I think it was in 2016. There was a very popular blog post by a physics professor on how to learn physics. And she went very deeply into the field because usually, yeah, we learn physics like in school, but when we grow up, so we are not motivated by the marks. And she wrote very extensively on the resources. The name of the person is Susan Rigetti.
I'm going to try.
Yeah, I will write it down there. But the thing is that after this successive blog post on physics, she wrote the same on mathematics. And the list is actually huge, because if you, it's not only enough to just go maybe through the equations, because probably, as what we learned today, it's real life problems, and sometimes we need some motivation to study math in the first place, not just in the sake of solving the equation, but in the sake of understanding maybe something bigger. And for that, I really recommend this Susan blog. I think it's very undervalued, but yeah, you can Google basically Susan Rigetti, and I'm writing it down now. It's S-U-S, Susan Rigetti. And the blog is So You Want to Study Mathematics. So find it on your website, and you'll get a huge list of the recommendations of the learning paths on the popular books, on the mathematical books, etc. So I think you'll find your personal website by Googling.
Awesome, thank you. Now I wish I had Googled so I could have used it. Any other recommendations?
Okay. We'll take, due to time restrictions, I have to follow strictly, I have to stick to time. So we will take one more recommendation.
Everyone who does recommendations, when you're leaving, just write it on this. I will put everything on the slides, and then I will share the slides with the recommendations. Let's do it like this.
Great. That would be also great. Or put it on Discord channel. That would be also helpful. Thank you, everyone.